The Relational Properties of Mass by Albert Einstein. I'm not going to claim this model. This is all Einstein's doing, okay? The only thing that I've done here is pointed out that you can't use homogeneity. Now, this results in an internally consistent cosmological model, but there's so much more. You can build a static and stable model that beats lambda CDM just by getting rid of that one assumption, homogeneity. You have to use a scale-dependent mass density profile. Now, we're going to get into all this. There's a lot to cover. We're going to try to do this in a time-efficient manner. I'm going to talk freely because if I read, like I have things written down and I've tried to read from it, it doesn't work out that great. I'm going to work directly from my website. You can visit it, theuniverseisnotexpanding.com. You can follow along if you want. So the relational properties of mass is this idea that space-time is not a real thing. It deserves no ontological standing. It's not a physical substance, whereas mass and energy are physical substances. Space-time is an arbitrary human creation. I guess it's not appropriate to call space-time arbitrary because we have it defined, but it's arbitrary as far as the numbers go. We can assign whatever properties we want to space-time. So that's what this first part is explaining. I write that it's an abstract apparatus used to measure things. It is a phenomenon that's more similar to currency, speciation, laws, and proper names than it is to mass and energy. The physical world has intrinsic properties, whereas all of the properties of space-time are assigned to it by humans. Okay. Now, there are real consequences of this. There are real issues to viewing space-time as a physical substance. Issues like the vacuum catastrophe, the dark energy anomaly, or the cosmological constant problem, coincidence. There's lots of problems when you have the wrong physics. The way I've resolved this is you just pretend that space-time is human created. That's the gist. That's the thing that ties all of my research together. We don't need space to expand. Okay, dark magic is not only unnecessary but entirely inappropriate for this situation. We should use physics, not magic. So the observations don't actually show that the universe is expanding. The observations show that there is a redshift in starlight that is proportional to the distance from Earth, from the observer. Now, there's other ways of redshifting starlight, but the one that comes along with general relativity is the one that I prefer to use, gravitational redshift. So how do you formulate a cosmological model using gravitational redshift? Well, it's extremely easy. You just have to assume that gravitational boundaries are arbitrary things. That space-time is not a real physical substance between, the space-time is not an object that is between Earth and the sun. There's no boundaries. The fact that we call the sun and the Earth is because it appears that there's boundaries. Like the density, the mass density between the sun and the Earth is very low, and so it gives the impression that there's these arbitrary boundaries, but there are no boundaries to mass. All of the mass blends together. Now, especially if you combine this with quantum field theory, then yeah, it's all quantum fields. All of the mass and energy are quantum fields. But even better, within general relativity, the space-time energy the energy that gravitates through space-time has mass in itself. And so even general relativity doesn't assume that space-time is a physical object. So what do you replace this magical, mysterious black stuff with? Well, you replace it with a scale-dependent mass density profile. It sounds complicated, but it just means that mass density requires a unit of volume to be able to determine. It's scale dependent. Okay, the mass density of an object depends on its size. So you can talk about the mass density of the star, like a star, like the sun. That's fine, because when you refer to the object called the sun, you are drawing an artificial boundary around a region, and you're defining the mass density of that region. And that's fine. That's totally legitimate thing to do. It's not actually, it ignores the rest of the mass in the universe. You're only talking about a specific portion. And when you create this artificial boundary so you can define the portion, like I say, you're ignoring the rest of the universe. But if you extend it out, eventually there is a common profile for all objects, depending on the size. You have to extend out on a cosmological level before there's a consistent profile. But eventually the mass density follows a pattern. And the pattern that I've found is this K over R. Okay, the K actually is just 0.833 kilograms per meters cubed, or meters squared. Excuse me. So what I mean by this is, if you draw a line of any length, of sufficient length, let's say that, not any length, it's got to be cosmological scales, that the profile will follow this. And the reason is because it's hard to describe this without talking about space. I just spent 10 minutes telling you how space is not real, and now I'm about to say there's space between objects. It's what I mean by that is that there's a lot of variability in mass density. Okay, it looks like objects have boundaries. It appears this way. It's because there's lots of other small, little bitty, tiny pieces floating around, and there's space in between objects on all scales. And if you zoom out and include, anything larger than 1 megaparsec, you start to see a pattern develop. And like I say, if you use anything several megaparsecs in length as your radius, the volume of space will have a mass density that is inversely proportional to the chosen radius. So the larger the larger the volume, the larger the radius, the larger the line that you draw, you'll have a lower mass density. And that's all this is. That's all this chart represents. I use gravitational redshift to explain the cosmological redshift, the Hubble redshift. The way that I do this is it's because objects are nested in other objects. Stars are in galaxies. Galaxies are in clusters. Once the light leaves a star, it begins to redshift from the change in the gradient, because near the star is the densest region the light will ever see. As the light travels away from the star, it encompasses a larger and larger volume, or a larger and larger region of influence begins to shape the geometry of the area that the light is encompassing. And so as this light increases in volume, there is a lower and lower mass density. So the gravitational redshift ends up being linear. It appears to be linear, just like gravitation, or just like the Hubble shift. We can totally match this K over R profile is perfectly in line with Hubble's law. When K equals 0.833 kilograms per meter squared, that's where we can get that 72 kilometers per second per megaparsec. Now, my formulation, I'm just using the Schwarzschild metric. The reason I'm using the Schwarzschild metric is because the universe is spherically symmetrical. On the largest scales, the universe is symmetrical. After a 1 megaparsec or so, the universe is symmetrical. There's just so many galaxies everywhere that it is essentially symmetrical. And so, Birkhoff's theorem kicks in. Anytime you have spherical symmetry, use Birkhoff's theorem. It is a little different because we have to accommodate both all the types of gradients and all the types of emission locations. And so that's not really that big of a deal. Like I say, we just use the Schwarzschild metric, but there's a little bit, if you look at the equations here, there's a little bit of difference. I'm just mainly wanting to show the null geodesics. I'm not interested in perturbation analysis or stability or anything like that right now. We'll get back to that in a second. But this all ends up being an observer-dependent horizon. Okay, that's because the emitting object is the star, where we can choose the coordinates. We can place the star in our chosen coordinates, in the center of our chosen coordinates. A horizon naturally develops because we assume Birkhoff's theorem. All of the mass contributes to the potential. All of the mass that's in the region between the observer and the emitter influences the potential of the emitting star, and that's what Birkhoff's theorem tells us. This gives us the distance proportional Hubble redshift and a horizon around 1.29 times 10 to the 26 meters, which is around 13 something billion light years. It's the same as the Hubble radius, I think is what you would call that. The look-back distance for the age of the universe. Here's the redshift formula. And so we also have a blue shift. I try to include caveats to remind people that there's another perspective. If you are in a void, if you are in the least dense void, then it's all going to be a redshift. Like, there's no way for it to be. There is a way. I'm trying to say that it depends on your location for sure, whether how much is redshifted or blue shifted. But for almost all locations, it's going to be insignificant for the majority of cosmological star lot. It's going to be a redshift. But it is possible for you to receive a blue shift, a distance proportional blue shift. We'll get to that in just a second. So here's this Hubble constant. It's 2.33 times 10 to the negative 18 hertz, or 72 kilometers per second per megaparsec. And so it also results in a uniform gravitational acceleration. This profile basically reproduces MOND. It's a little higher than MOND, though. It's 3.49, whereas the MOND constant is 1.2. I may discuss a little bit of that later on in this video. So the amazing thing is that this density profile, this coupling constant that I'm using, K, like I said earlier, it's 0.833 kilograms per meter squared. What's amazing about it is that it's not just pulled from anywhere. I mean, for me, the way I found it was I just worked directly from Hubble's law, and I fine-tuned everything until I got it right. But the surface area, or the surface density, if you define surface density as mass and horizon, mass divided by the horizon area, the total mass of the observable universe divided by the horizon surface area that it creates is this k divided by 2. And I think the reason that it's divided by 2, I think, is because you have to have room for 2 horizons. I'm not exactly sure. The quantum field theory stuff gets a little crazy, and I'm not really on the up and up with the horizon, with the holographic theory, holographic principle. But I think this has a lot to do with that and quantum field theory. We'll get into that a little more here in just a minute. So now the cosmic microwave background radiation, the way that I use, this is where the blue shift comes in. This is where the 1 plus z now is the observer is centered. It's the other perspective because it's not starlight. See, starlight is redshifted because the star is the massive potential. So Birkhoff's theorem would tell us that everything goes to the center of that star. All of the potential in the region of influence, if you have spherical symmetry, it appears as if that potential is in the center of that star. And so it's, if you have the other perspective for that is if you were at the center of that star. Just imagine if you are on the surface of a star and you're looking at Earth. Now you have a blue shift coming in, like, because the light has to is traveling downhill towards you. And so it's like a ball rolling downhill. It's picking up speed, kind of, so to speak. It blue shifts depending on the distance of travel. The same thing would be for the cosmic microwave background radiation. That's because that I am interpreting this as blue shifted Hawking radiation. The reason that it's Hawking radiation is because we have a horizon, we have a coordinate singularity, and so the principles of quantum field theory kick in, or whatever. The 1 plus z is so extreme near the horizon that it's as if radiation comes out of the vacuum. This is not coming out of the vacuum, actually. It's coming out of the quantum fields. Okay, that's because we're using the relational properties of mass, and we're not considering space-time or the vacuum as a thing. The vacuum is the absence of things. Well, when you have the absence of most things and you have just the general quantum field, it produces the 1 plus z for this region produces the Hawking radiation. This Hawking radiation is very cold when it's emitted. It's this 1.42 times 10 to the negative 30 Kelvin, just absurdly cold. Well, at that region, there's exactly enough 1 plus z to redshift it to the 2.725 Kelvin that we see in the background radiation today. What's amazing about this is that you have to fine tune it. Now, it's very hard to do. It's a very sensitive calculation. If you just use a standard calculator, it's probably not going to be precise enough. You have to use high precision software, and it depends on the software how the calculation ends up. It's really annoying so I don't know. What I've found is that at 3.48 times 10 to the negative 35 meters from the horizon, so this is basically 2.15 Planck lengths. That's where we get that 2.725 Kelvin. So I've got a calculator that I've made. Where's it at? All right. So this is on the website, and I used JavaScript, and I used high precision JavaScript, and so it's slightly different. Here it's 3.49 times 10 to the negative 35. I don't know what to tell you. I don't know which one's right. Very near the horizon. Okay, I thought it would be 1 Planck length from the horizon. And so in previous videos, I sat there and discussed, I forced that 1 Planck length. For one, we don't know if the Planck length is actually a real unit. This would be the new Planck length. Now you could use the Planck length because there's an equation. It's a basic equation. It's hg divided by, what is this? Square root of h bar times gravitational constant divided by c squared or c cubed. I'd have to look it up. Anyways, there's a fundamental equation that defines the Planck length. And the Planck length is kind of also the minimum unit of length in physics. And so this would be the new minimum length. It's so esoteric and stupid. Physics is so stupid. Just listening to myself, it's so absurd. Regardless, this is our minimum length scale, okay? And here it's 3.49, and why it's 3.49 times 10 to the negative 35 is because that's how we get the 2.75. So I can change this if I want. We'll make it 3.40, and you see we get 2.75. And we can just go to 3. Let's see what happens at 3. It's 2.07. Or 2.9, sorry. It's 2.933. So this depends entirely on the measurement of the CMB temperature. Now there may be something in quantum field theory that tells us that very near the horizon at this distance, I assumed it was 1 Planck length, and it very well may be, just because no matter what calculator I use, they give me a different measurement. So I don't know. This is up in the air still, but the theory, the equations behind it are still solid. Whatever it is, it's RS divided by R. Now let's go back to this. Where are we at? Here? I'm going to take a second. So because we have a minimum and a maximum length, we can now do some real stuff. Okay. So here's the vacuum energy density. The vacuum catastrophe refers to it's the worst prediction in physics history. So it basically says that all of the 0-point energies of all quantum fields for all possible modes should sum up to X amount, and they're wrong. Okay, they measure this through cosmology, and quantum field theorists should start attacking cosmology hardcore, because they're right and the cosmologists have been wrong. If we use this coupling constant K and the CMB minimum length, the minimum length we just obtained from that, and the maximum length that we obtained from our horizon, we can first of all describe the vacuum energy density as scale dependent, which it should be. And this gives us some cutoffs for the IR and UV spectrum. Here are those cutoffs. It's just the horizon, and like I said, if the calculations are correct, 2.15 Planck lengths would be the UV cutoff. And then this results in the whatever you call this. I don't know what you call in quantum field theory. The vacuum energy density. This is like we can solve the Einstein-Hilbert action, and we can get this. And so we can regularize general relativity. So this is quantum gravity. General relativity is regularizable, or I think this would be, is it regularized or renormal? I get those terms confused. One of them. It makes it compatible with quantum field theory. That's what this is. I don't even know if it's regularizable or renormalizable right now because I've got a microphone in front of me, so my brain doesn't work quite the way it should. But this is quantum gravity. It's just so ridiculous that a hillbilly figured this shit out, and the Ivy Leaguers are like, whatever. All right, so we can test the model using. I use DESI. I don't think there's much better to use, but so there's this thing they found this pattern that they can use to make a distance ladder. Cosmology is so stupid. But it's this pattern. They call it BAO, baryonic acoustic oscillations, I think is what it is. They call it, it's so absurd because like it takes forever. It took me like 3 weeks to figure out what this shit was because they talk about it being sound waves from the early universe. And I'm just like, that doesn't make any sense. What is it? And then they just always refer to sound waves from the early universe. Anyways, once I figured out what it was, it's just this pattern that they found in the distribution of galaxies. Anyways, they can use it to test the model. And you get this Alcock-Pazinski ratio, which basically tells you how strong your model is when you test it against these results. Now, I had to use ChatGPT, and ChatGPT kept hallucinating. I hate using AI so much because they just hallucinate shit. Now, it was hallucinating values that were very, very close. Very, very close, but I end up having to just do it manually myself because the values, it would never use the correct values. I don't know if it was like it was thinking it was a copyright violation or what, but regardless, I had to use a lot of ChatGPT, so I used ChatGPT's method, and I'm pretty sure this is right. After it took me, it took a long time to figure this shit out. So, this is pretty well right, but I'm just like I copied and pasted this from the ChatGPT thing. So like I'm just making a statement that this part right here may I checked it over though, but I had to, like I say, like the first 10 times it would just make the numbers up. Now it was always really close, but it was like simulated data every time, and so I had to copy and paste the actual data in. And then I got it to formulate. The reason I used it for this is because LaTeX. I want the equations to display correctly, and LaTeX is retarded. And plus, this table is hard to do. Anyways, that's my caveat for this. But I pretty well crush Lambda. Not really, because Lambda wins the first 3. But look how close I am. So this is me. Or let's say Albert Einstein. This is Albert Einstein's static model, and this is the Dark Wizard's model. Early on, I do bad. I think that this 10% is indicated or indicative. I think that this is caused by something that is not so. I think that this is not on the up and up. I don't think I'm that wrong. I don't think I'm 10% wrong, 9.1% wrong. Whereas Lambda CDM is 8.5% wrong, okay? At this distance, at z equals 0.7, I'm 5% wrong, and Lambda's 4.6% wrong. So I'm still getting crushed. At z equals 0.93, I'm 3.5% wrong, Lambda's 2.5% wrong. Okay, I'm still getting beat, but here's where I start picking up. And I am 0.1 off on z equals 1.3, and at z equals 2.33, I am 0.2% wrong, whereas Lambda is. And this is going to continue, okay? There are more to do, and I win on all of them. And this doesn't include dark magic, dark energy, none of that stupid stuff. No inflation, no Big Bang. This is just exactly the most intuitive model, and it beats lambda CDM. And so there's a replication checklist if anybody wants to do this themselves. This is all on the website. Here's the CMB calculator again. Oh, are we done? Galaxy rotational curves. Oh, dark matter. Yeah. This one, I don't know, man. I don't know what to say. My profile suggests the galaxy rotational curves should be rising. Let me explain what this is. So if you look at a galaxy and you measure the velocity of each star going around the galaxy, there should be a declining velocity as you go out. So the velocity should be low on the edges of the galaxy. However, that's not what we observe. Vera Rubin, I don't know, back in the 80s, I think, she found, this is the way the story is told, I don't know, but if you look it up, if you look dark matter up on Wikipedia, Vera Rubin, but there was other people too, so that's why I say all this. But she found that there was this flattening of the velocities. The reason that it's flattening, they don't know. So they said that if there was more mass, it would be flat. So it's dark matter. Doesn't make much sense. Dark matter is not necessary. My profile predicts that the curves should be rising. Now, if they always say that it's flat, but if you start looking at all of the galaxy data, if you start looking at it all, you start noticing that most of them are slightly rising. Now there are a few that dip. It seems like the biggest, most giant galaxies dip in speed or velocity towards the edges. And is it speed? It may be orbital speed instead of velocity. Wow. No, it's velocities. Depends on if you're talking about a single object or not, though. And it's all like, that's the object thing. It's all arbitrary. It's speed and velocity are arbitrary in this sense, because a galaxy is a collection of objects, but so the hell is a star. Anyways, I just had a brain fart there. What were we talking about? Dark matter. Yeah, we don't need dark matter. That's just the curve should be rising. And if you look at all the data, most of the curves are rising. Now, there's some that are different, but, I've developed a cosmological model. Like I said earlier, it's anything over a megaparsec. Under a megaparsec, like galaxy size, this is not really my job. It's not really the job of the cosmologist to be talking about orbital speed of galaxies or orbital velocities. It's not. That's an astrophysicist's job. I mean, look, there's galaxy evolution and whatnot, but just line all the galaxies up from least dense to highest density, or from lowest mass to highest mass, and that's your galaxy evolution. You don't really need to be doing lots of theoretical work in this area, because it's extremely complex stuff. You really just need to be following observations, in my opinion. And so that, I don't buy too much stock into this, but what's amazing is that I do predict rising curves, which is a step in the right direction, because basically I just eliminated 60% of the data problems. And so now you have to explain the largest galaxies and why that they have a flat curve instead of a declining or a rising. And, it's because their core is very dense compared to their exterior. I don't know. And it's it's changed over the past. I don't know why. Honestly, it's not that big of a mystery. I've removed 90% of the mystery here. It's just galaxy dynamics at this point. Basically, essentially, what I've done is I doubled the Mond parameter or the Mond constant, and I provided a theoretical support for it. And so it's this is annoying. That's all. That's what this is. This shit is annoying. This shit is super annoying because I'm not even sure that there's an anomalous flattening of spiral galaxy curves. I'm not even sure that's real. It appears to me to be an artifact from averaging. Look, if you find a galaxy that has a flat curve, it's not that big of a deal. And if everyone you see has a flat curve, it's not that big of a deal either. It definitely does not mean that there is a new mysterious exotic matter. That's so stupid. I can't believe publishers still talk about dark matter. Like, it's embarrassing. And annoying because like how are you supposed to solve that problem? Like, it's not a problem. This just takes some simulation. This is the work for artificial intelligence. Artificial intelligence is going to absolutely destroy cosmology here in a few years. It is absolutely going to destroy it. I promise you, artificial intelligence is not going to put up with this shit. I can't promise you that because artificial intelligence is pretty terrible right now. But if it becomes smart and it finds this and it thinks, oh, parsimony is the way to go, then it's a good scientist. We'll know if AI comes out and says that Chris Brown's right, the universe is not expanding, then you can trust it then. No, never trust AI. Never ever trust AI. It's not a trustable thing. This is just a Birkhoff's theorem simulation that you can just work through visually. Some people have a hard time with understanding why there's redshift and why there's blue shift, and so I don't know. I made that. Here's all of my relationships. Most of these are solving for the coupling constant, but just to show you how amazing this model is, that everything just ties together perfectly. Yeah, and then here's some frequently asked questions. I don't think there's anything after that. Yeah. All right, that's it. Y'all have a great night. That is the sound of me opening a new Belgium honey orange triple. It's a Belgian style ale brewed with African honey and fresh ground Seville orange peel. It's amazing. Seville orange peel? Seville. Yeah. 30 seconds in, not said a damn thing yet. Should I stop it or keep going?